Hello, everyone.
Hello. How are you?
Doing good. How are you doing?
Okay, it's time to start. Good afternoon, everybody. Thanks for joining today to our second round of TRANS-IPIC monthly research webinar. We started this series about last month, and every month we have two consortium members of our centers to present an update and a progress of the research activities that the centers is considering for their research programs. And today we have two speakers. The first is Islam Radwan from University of Texas, San Antonio. He's going to brief us on some of the current work on the one of the funded projects through TRANS-IPIC. And the second presentation following that is Dr. Wang from Purdue. That's going to cover the second half of the webinar. And the way it starts is that we will split this. It's a 1 hour. We'll have the first half an hour to cover the first presentation. It's about 20 to 25 minute-ish, and then followed with Q&A. And then we're going to move on to the next presentations. With that being said, I will introduce here Islam. Is currently a PhD student at UT San Antonio, and he has a master's degree from Construction Science and Management from UT Rio Grande Valley. Joined us last year, and he has a lot to say about his work in the cool pavement. Islam, please go ahead and share your presentation.
Yes, Dr. Samra. Can you see my screen?
Yes, I see it.
Hello, everyone. At the beginning, I just want to thank you, Dr. Samir, for introducing me, and thanks everyone for coming today. And today I'm gonna speak about our current research project that is being funded by the TRANS-IPIC, and we are working here at the University of Texas at San Antonio. And our project is for cool pavement for mitigating urban heat island effect using the phase change material in precast concrete. The outline for the project, for the presentation, we're gonna first go through the inspiration. So what inspired us is one of my previous projects for my master's degree. It was related for electrically conductive rigid pavement. And also I will, secondly, I will go through the cold pavement for mitigating the urban heat island. And it's gonna be divided into introduction, research goal, and scope of work, experimental work, finite element work, and expected results. The inspiration. So as I have mentioned, that project was my master's degree. It was done at the University of Texas, Rio Grande Valley. And my supervisor over there was Dr. Muhammad Abdurrahim. And that project was using the waste rubber tires as a new sustainable material for electrically conductive rigid pavement. The main goal for this research was to melt the snow. And I will go through these pictures very quick. Rubber pads. And then after we made sure that these rubber pads can act as a heat source, we embedded them inside the concrete sample. So we made two samples, as we can see here, one concrete sample with one rubber pad and the other with two rubber pads. Those some of the results that we got them, and for the combined sample one, as we can see here, the difference between the temperature of the surface temperature between the surface, the original one, which is the 23 Celsius, and after 60 minutes, we can see the difference. So the averages for the top and the middle and the bottom, we can see there's it's 40 Celsius, 38, and 36. The same thing for the combined sample two. We also did an experiment for snow melting. And as we can see here, for the combined sample one, after 60 minutes, the surface was completely dried while using ice cubes. The same thing for combined sample two while using crushed ice. After 40 minutes, we can see the snow disappeared. So that project actually motivated us to keep working on solving the thermal problems related to precast concrete or the rigid pavement. So getting back to our current project, which is the cool pavement for mitigating the urban heat island effect using the phase change material in precast concrete. So at the beginning, what is the urban heat island? The urban heat island are the areas in the cities that are significantly warmer than the surrounding rural due to the urban developments. Some of the studies, they say that the ambient temperature of 450 cities increased due to the urban heat island phenomenon, which can negatively affect the energy consumption, the environment, and people's health. The same thing for the some of the forecasts of future cooling energy consumption related to residential and commercial buildings. They say that by 2050, it may increase up to 750% and 275% due to the local and global climate change, and also the expected rise in cooling system. So what causes the urban heat island? Some of the main reasons here, for example, the surface properties. We can see the urban heat areas have heat absorbing surfaces such as the asphalt or the concrete. Also the low albedo of these surfaces. So the expression of albedo, it means that the ability of the pavement to reflect the heat. So the lower the albedo, the more absorption by these surfaces. Also the urban infrastructure, the more buildings and structures, the more heat and airflow will be trapped. The human activities such as the transportation, industry, and of course the loss of vegetation, the deforestation and the urbanization reduce the cooling effects. And also the more air conditioning and heating, those are gonna generate additional heat. So what can be the consequences for the urban heat island? Of course, the infrastructure damages because the extreme temperature cause thermal stresses, which can lead to cracks, wrapping, and compromise the integrity. Of course, it's going to result in overall higher temperature within the cities. Also, the health risks, so elevated temperature increase the risk of heat-related illnesses. Also, the air quality, the higher temperatures, the more acceleration of the formation of pollutants, higher energy consumptions. Elevated temperatures will require more usage of air conditioning and cooling systems. Also, the human comfort will be affected. So the higher the temperature, it will result in discomfort and fatigue and reduce the productivity of working. So the surface heat islands, a study for Akbari and Rose, they found that between 29 and 39% of the urban heat island effect related to the paved surfaces. Therefore, the impact of the pavements on urban heat island development is significant. So that's why working on cooling the pavement is going to contribute to solve the urban heat island effect. The cold pavement strategies, a lot of researchers, they conducted several cold pavement strategies in their research. For example, some of them, they're working on reflective asphalt pavement or reflective concrete pavement. And in this way, they try to increase the albedo of these surfaces, or they increase the reflectivity of the surface. Some of them, they work on making the pavement porous or permeable, also the water retentive pavement. Some of them, they work on heat harvesting pavement by extracting the heat or by taking advantage of this heat, or making the pavement thermally conductive by adding thermally conductive materials such as the carbon fibers or carbon black powder, or even metals sometimes. However, one of the most promising way to cool the pavement is the integration of the phase change materials. And the phase change material has unique characteristics of the heat capacity. And that's what I'm gonna describe in the next slides. So the phase change materials, what is the phase change material at the beginning? Is a heat fusion substance that melts and solidifies at a certain temperature. So if we can look at this curve, the temperature for the phase change material increases while the heat increases as well. And this phase is called the sensible heat until it reaches the melting point, which is 20 Celsius. At this point, the main characteristic of the phase change material works, which is it starts storing the heat, and all the heat will become latent heat. And this is the main characteristic that we are trying to take advantage in the pavement. We are trying to increase the heat capacity of the pavement. We are trying to make the pavement store the heat, and we are trying to make the pavement temperature constant at this temperature as much as we can. So some of the application of the PCM, the phase change materials are existing as products in the market. So in the building construction, they use it for insulation, roofing materials, for thermal energy storage, they use it for the solar power plants, for the textiles as well, the sportswear for temperature control and comfort, also for electronics cooling, food, beverage industry, the automotive industry, and the medical application for the temperature controlled storage for biological samples. So the phase change material can be divided into three main types: the organic ones, and the inorganic, and the eutectic. Worth noting here that in our research, we're using the organic and the paraffin. The reason why behind this, because one of the advantages is for the organic is it's chemically stable, and also it's being strongly recommended for construction materials. And for the inorganic, it's corrosive to the metal, so I don't think it's gonna be effective when you use it for precast if the precast is reinforced. So that's why we're using the organic for that purpose. On the other side, researchers have developed 4 incorporation methods of the PCM in order to use it inside the concrete. The LWA is the lightweight aggregate. They use the porous aggregate and they immerse the PCM in liquid state inside the porous aggregate, and then they use the aggregate to make the concrete. The shape stabilization PCM, it's similar than to the LWA, but they use the graphite as a supporting material, and they immerse the phase change material in liquid state inside the graphite, and then they use the graphite inside the concrete mix. The third way, the macro encapsulation, they use the phase change material inside the pipes or inside sheets, and then they use it for different purposes. The fourth one is the micro encapsulation. I want to highlight here that we are using this way in our research. The reason why behind this, because the product, it comes in powder, which is going to be easier if you want to use it in the concrete mix. So that's why we are using the micro encapsulation. So research main goal and the scope of work. As I mentioned, this study aims to explore the integration of the microcapsulated phase change materials into the rigid rigid precast concrete pavement. And if you can see here, the picture describes exactly what we are trying to do. The phase change material is going to be inside the precast concrete, and here's the mechanism of the PCM. As we can see, the PCM is going to be in solid state, and once the temperature goes up, the latent heat phase is gonna start, and then it becomes completely liquid, and then the latent heat becomes sensible heat, and then at night, while going back to the solid state, all the stored heat is gonna be released, and that's what we are trying to obtain. Our scope of work is gonna be we are working on experimental phase, and also we are working on finite element model by using the Abacus software, and also we are initially we are working on the sidewalks and the curbsides. So we can divide the experimental into four phases: the setup, the material, and the physical material integration, and then the equipment. This is an schematic heat simulation setup of the experiment that we are trying to build. As we can see here, it's a slightly big chamber that is surrounded with aluminum wrap and insulation. We do have two stands. Each one of them has two light bulbs. They are going to act as a heat source on the surface of the two samples. We have PCM concrete sample, and we do have control concrete sample without any PCM. And both of them are going to be connected to a data acquisition system by sensors to monitor the rise in temperature and also the rise in heat. The first thing we did that we contacted a company, it's called the Microtech Laboratories, and we gave them a brief about our project, and they gave us recommendations for two products. I just want to highlight here that the two products are microcapsulated already. And one of the main factors that we are that we took them in consideration when we were selecting the types of the PCM is as I mentioned, the dry powders, because we need the PCM in powder, and also the melting point, which is 28 Celsius, and this is one of the critical factors when it comes to PCM selection, and also the heat fusion. The same thing for the MPCM 28 and the Micronal 28. Those are real pictures for the PCM packages. This is the Micronal, and this is the MPCM. For the we are restricted for the concrete design mix. We are restricted to the TX specifications for sidewalks and curbsides, and those pictures are from the manual from item 30. And these pictures are taken from the manual item 360 in concrete pavement. And as we can see here, we use the class A for curbsides and sidewalks. And also we took in consideration the grade, which is the aggregate grade, which is grade 8. Those are real pictures of the mixing. On the right-hand side, we can see the control concrete sample with 0 phase change material. We use the ratios 1 cement, 2 sand, and 3 gravel, and 0.6 water ratio. And also the coarse aggregate grade was grade 8. And on the left-hand side, we can see the mixing process of the PCM. As I mentioned, the PCM is in powder form, and we added at the last step because it was strongly recommended to add the phase change material at the last step in order to avoid breaking the shell of the microcapsule of the PCM. We made two PCM concrete samples, the 5% and the 10%, 5% of and 10% of the total weight of the control sample. And then we have 3 final concrete samples: the 0 phase change material, the 5 phase change materials, and the 10%. Okay. And then those are the 2 stands, and each one of them has the 2 light bulbs. So for the heating source, as I mentioned before. On the other side, working on the finite element model, as we can see here, this picture describes most of the interactions, the heat interactions on the pavement. So between the layers, between the concrete layer and the base layer, there is a conduction. And also between the base layer and the sub-base layer, there is a conduction too. The interaction between the concrete pavement and the atmosphere is called the convection. I just want to highlight here that one of the most important and critical step here for the modeling on the finite element modeling is defining the material properties, because after adding the fissure material to the concrete has new thermal properties. That's why we went to the second step to measure these thermal properties for our samples. As we can see here, we do have two devices. The first one is the differential scanning calorimeter, is the DSC, and this device used for measuring the specific heat capacity. And the second one for the laser flash analysis, this one is used for the diffusivity. And if we recall the equation, the diffusivity equals the thermal conductivity over the density times the heat capacity. So if we can measure the specific heat capacity and the diffusivity, we can get the thermal conductivity. I want to highlight here that those are the main thermal properties that we need them to model the finite element modeling. The thermal conductivity, the heat capacity, and also the latent heat of the PCM, the melting temperature of the PCM2. This picture shows the process to prepare the sample to use them inside these devices. This is some of the initial model for the finite element modeling. As we can see here, here's the step for heat flux loading. And also we did two interaction processes, one of the day convection and also for the night convection. And this is the step for meshing. Those are an initial results for the model that we did. The picture at the top is for the day step, and the one at the bottom is for the night. We can see here the heat flux on top of the pavement during the day is less than the heat flux on top of the pavement during the night. And that's exactly what phase change material does. It delays releasing the heat until the night comes. Some of the expected result for that current research, of course, the surface temperature is going to be regulated due to the addition of the PCM, and also the heat capacity. As I mentioned, the heat capacity characteristic of the fissure material is really useful. So that's why if we add them to the concrete mix, the concrete sample heat capacity characteristic is gonna be increased too. And both of them are gonna affect the mitigation of the urban heat island. As I mentioned, the PCM absorb and store excess heat during the day and releasing it gradually at night. That's it. Thank you.
Dango.
Thank you, Islam. I just want to emphasize that this is still an ongoing project, and we had a late start in order for us to really line up what exactly we need to work on this. So currently, all the experiments have been set in place. The finite element model has been established, and we are in the process of collecting the experimental data and the computational data to put them all together to really reach out our conclusions about phase one of this study. And currently, we are still collecting more data, and ultimately, we're looking forward to integrate this modified concrete slab in sidewalk here on campus and see how that will have an impact on the strength side and on the durability side. So this is still up and coming, and I thank Islam for putting those slides together and sticking to the time. So I'm opening the floor for questions. I just want to mention here also that we have in the city of San Antonio, which actively engage in finding solutions to mitigate urban heat islands in the city. And one of the solutions they have tried right now is one of the options to mitigate heat urban islands that Islam mentions about painting the surface of the pavement with light color seal coat that has changing the albedo the pavement, and that increased reflectivity. The project actually concluded in December, and we had a very hot summer last year, and that really emphasized the importance of the work that the city does. While we're still finalizing the reports, but the result doesn't really show a significant impact on the overall reducing the surface temperatures by any means. This is by no far has any impact comparing to the shade that comes from the trees and the vegetations. But it was a trial towards that directions, but significance was not as expected. So we're trying to look into the making the modifications within the structure of the layer itself to mitigate that heat exhaustion at some point.
I have a quick. First of all, Islam, like great presentation. Thank you so much, and we understand how much time you had to put this together and the results here coming, given the delay that Samer mentioned, Professor Dessouky mentioned. So I really appreciate that. Great work, and good luck with the rest of the project.
Thank you.
One quick thing here that maybe some of our friends from the industry would ask is the scalability of this technology when it comes to scaling it up. Can you make a few comments on that?
Can you just repeat that the last thing, because I couldn't hear it.
Yeah, one concern always that the industry have is the scalability, the size of this technology and how actually can scale it up. Because when we are talking about, for example, precast concrete pavement, we're talking about different scale from your specimens. Can you make some comments about the ease of scalability and if there's any challenges that you can maybe identify, and whether that's going to be part of this phase of the project or maybe in future phases?
Well, at this stage, we're working on a small scale to see the impact of the PCM. So the technology of the physician materials, we are trying to take advantage of the heat capacity of the physician materials. So this latent heat characteristics, it doesn't exist in the original concrete without the PCM. Okay, so of course you're gonna have some challenges, because we still need to know how the physician material is gonna impact the compressive strength of the concrete or the mechanical properties. That's another path that we need to investigate to see how durable the whole composition, not only for the heat path, and it's gonna be also for the mechanical path, in order to have like a very big comment of if you can scale this up or not. But it's not only the heat path, it's only the mechanical path.
Yeah, let me add to that as well, that once we find out that this product or these materials has an impact, like Islam mentioned, yes, there is speed bumps along the way to scale this up. One of the keys for that we faced is the cost of these materials. It's costly. It's going to increase the cost of making precast concrete. However, we haven't seen a lot of literature that really have expanded the use of these materials. But once we found that there is a better use for it, and there is another application that can benefit from, I guess the manufacturers need to look into this to try to lower the cost of making these additive materials to it. From the constructability side, there is no issues. It's an additive that can be added like a regular admixture still to the concrete. So it doesn't change the way the concrete is constructed. It is the cost side to it. So I can see a challenge from that perspective. But again, at this phase, we're looking into, is it really worth going forward and expand it, or that's something that we might rethink about? So it's still a lot to answer, Basim, and we're hoping to get a preliminary conclusions about this part of it by the end of this year.
Thank you very much.
Any further questions before we move on to the next one? I would like to thank TRANS-IPIC for funding the study. I mean, it works really well with South Texas and all the help that we're getting. So anything really that can help, we really appreciate it. Air condition doesn't do much here as well. So the second presentation, Dr. Yu Wang is a PhD candidate in the School of Civil Engineering at Purdue University. And his research interests including developing functional architecture, cement-based materials using 3D printing technology. So we're moving from heat mitigation strategy in cold pavement to 3D printing technology. So Dr. Wang, giving you the title of Dr. Wang just to encourage you to get your PhD, and you will at some point be a doctor. And please share your presentation.
Yeah, thank you, Professor. Let me share my screen.
All right. Again, please make sure that we have about 25 minutes so we can keep some time for Q&A.
Okay.
So,
thank you. Hello, everyone. I'm Yu Wang. I'm working on the 3D printing concrete at Purdue University. So today I'm just going to talk about our project on the bio-inspired solutions for the roadside barrier applications. So we are exploring 3D printing technology as an alternative precast technology. And so let me, in the next probably 5 to 7 minutes, I'm just going to do a brief introduction about the roadside barrier. So what are the purpose of the roadside barriers? So the main purpose of the roadside barriers are basically to redirect the vehicle and deaccelerate the vehicle to reduce the risk of the vehicle to crashing into more dangerous objectives. And it's really, the structural performance is really important, and the material performance is also really important. In order to get the good structural performance, we need to leverage the strength, stiffness, and toughness of our concrete materials. And from the AASHTO road design manual, the barriers are categorized into three. There are three categories of roadside barriers. Flexible barriers typically are cable barrier and plastic barriers, and semi-rigid system like the metal guardrail or the rigid system. Typically, they are concrete barriers. They consider as rigid systems. So different kind of barrier have different applications. So as you can see here, they are used in different test levels. So different test level are before the barrier put into service, they need to go through the full, we call it full truck test. So the truck tests are leveled from TL1 all the way to TL5. TL1 to 3 are typically small scale testing with small cars and pickup trucks. And when we come to TL4 and 5, they are it need to be tested under the large trucks basically. So typically flexible system are kind of more forgiveness because of the flexibility and more impact energy can be absorbed during impact. However, consider the strength limit, it can only use under low level tests. If you see the table, they are mainly used under TL2 and 3. If we come to TL4 and 5, traditionally, typically we consider the concrete barrier because of its abilities to resist the high impact loading to better redirect the vehicle. And also in the table here, when we come to 4 and 5, there are a lot of different shape of concrete barrier. And concrete barrier have a lot of advantages like high strength, and is also cost effective compared to the other system. But all the concrete barrier are considered as a rigid system, which means it do not consider to absorb energy during the impact. It can only resist the impact load to redirect the vehicle. So can we augment the functionality of concrete to improve its energy absorption capacity of the concrete barriers? So there are currently some solutions. I'm going to explain a little bit more. So currently, their concrete barrier also have different shapes, like jersey barrier, F shape, single slope shape. They are like 5 shapes approved by the AASHTO. So how jersey barrier works, which is commonly you see in the highway. So when a vehicle right up to the barrier, it generates a lifting motion. The lifting motion can dissipate some of the kinetic energy to redirect the vehicle and also reduce the energy imposed on the cars. However, under certain situation, like if there's high speed or if under different impact angle, is have the chance to cause a rollover of the car because of the lifting motion. So how do we like address this drawback? How do we prevent this lifting motion? Maybe we can use other shapes, or we can improve the energy absorption capacity of concrete. So there are a different shape is the vertical shape, which as based on the design, it do not have a sloped shape to kind of lift the vehicle when it's right on it. So it can it can prevent the lifting motion, which can prevent the rollover of especially on large trucks. But if we drive on the highway, we typically do not see the vertical shape. This is because it do not generate the lifting motion, which means most of energy are imposed to the car, which will cause more damage to the car compared to the jersey barrier. And if there's a high impact loading, there will be a like we can call it hand slap, which if there's high impact lateral impact force, the passenger's head will like pass through the window, and if the barrier is tall, it also have the possibility to crush with the concrete barrier, which is really bad, which it can cause the death of the passenger. So this brings us to the point that the existing concrete barrier is like strong enough to redirect the vehicle to get the vehicle back to the lane, but it's kind of have a drawback to protect the driver and passengers. So that's bring us to our point. Can we improve the energy absorption capacity of concrete barrier? Can we augment the functionality of our concrete to improve the energy absorption of the concrete barrier to protect the driver and passengers? There are a few current study and current solutions, like in here, the Department of Transportation of Nebraska, they did a study. They attached some rubber cylinder in front of the concrete barrier. So during the impact, there will be more deflection, so more energy will be absorbed. However, because we add another layer of material, the rubber and the metals, it add another layer of cost. And also, after each impact, it will have plastic deformation. So which means after each impact, you need to replace the system. Also, there's another system that approved by the AASHTO is the, like you see here, they call it cushion wall system. So when there are like high frequency of impact, lateral impact, this system can be used in the design. However, this as you see here, it take a lot of the roadway, a lot of the space on the shoulder, and you need to replace it after the impact. And also, there's another study about using engineering cementitious composite for the energy absorption capacity, so energy absorption purpose, from the Louisiana Department of Transportation. But engineering cementitious composite is also a kind of expensive material. So none of these are really widely used due to different limitations. So can we augment the energy absorption capacity just for the concrete? So we don't add rubber and we only improve the energy absorption of concrete. So how do we augment the functionality of concrete? Like for example, for a rigid concrete barrier, because of the stiffness, the energy absorption capacity is really limited. But can we have our concrete barrier to absorb more energy during an impact so we can protect the driver and passengers? Luckily, in nature, there are a lot of examples. So nature used the brittle material. However, there are a lot of material can still resist impact force, like the lobsters, like the monkey shrimp or nakers. They are all kind of stiff material, but it can still resist impact loading. So how have we use what we learned from nature to augment the functionality of concrete to improve the energy absorption capacity of concrete? So first, of course, we start with the loading condition. We want to improve the impact resistance. We come to improve the energy absorption capacity. And then we learn from nature of what is the microstructure and what is the material of the organ of the different animals. And then we study what is the mechanism, what is the real damage mechanism for that to improve the energy absorption capacity. And there are a lot of structures already been found for different applications, like the helicoidal or gradient or cellular structures. And there are also there is also an example damage mechanism. For example, for brittle material, there are always a fatal crack. However, for the biological material, because of the presence of the interface and because of the clever architecture arrangement, so it can promote the micro crack development. So it can improve the toughness and improve the energy absorption capacity. And then for 3D printing concrete, with the layer by layer manufacturing process, we always impose the defects and interface in our system. So this kind of give us a chance to take advantage of these interfaces, to take advantage of what we learn from nature to improve the energy absorption capacity of concrete. So like for the bio-inspired design, typically a little bit complex than the normal concrete, which means for the traditional cast construction method, it will be hard to manufacture these designs. But for 3D printing concrete, it gives us this opportunity. So because basically we use digital manufacturing technology. The only thing we need to do is manipulating the toolpath with the concrete material. So this will give us different architectures and which can enable new functionality of the concrete. So now I'm going to talk about a little bit about with our work. We start in small scale, and so the small scale work motivation from the monkey shrimp is a dotted club of monkey shrimp. So if we take a cross section of the claws of the monkey shrimp, it gives us a cross section like this, and the monkey shrimp can smash the snail in using really high impact force in 0.1 second. So how this claws and dotted club absorb these high impact energies. So if we run the simulation for the impact behavior of the monkey shrimp, so we can get a stress distribution contour in here. So in different region, there are different architectures. Like in this green region, the researcher found there is the architecture, we can call it bully architecture. And then in this blue region, which is undergo high compressive stress concentration, there's another architecture, we can call it the sinusoidal or helicoidal architecture or herringbone architecture. So can we use this architecture with 3D printing concrete to improve the energy absorption capacity of concrete to provide our concrete with a novel functionality? And we start with Boolean architecture. So to study this Boolean architecture, there are two steps. The first step is to replicate the structure, which is relatively easy. We just need to design the toolpath. However, the second and the most important part is to replicate the key mechanism of this architecture. So the key mechanism is, we can call it the interfacial twist crack mechanism. So in the dotted club of monkey shrimp, they have fiber and matrix with high anisotropic properties. So it aligned with the pitch angle between each layer. So when a crack initiates, it can generate a twist crack. And when they are high, when our sample have a large volume, which means we have a high volume of interface, so they will this structure will promote damage delocalization, will promote the more micro crack development to improve the toughness of the sample. So we start to figure out how to replicate this key mechanism, since it's really important. So first, we need a high anisotropic material. We found that when we 3D printing concrete with fibers, the fiber are like preferably to align during the printing process, which means if we print in different filament orientations, we will get a high anisotropic properties. So like in here, for the 90-degree and 0-degree sample, if we test in a 3-point bending test, we will get a significant different flexural stress. So taking advantage of this high anisotropic, we print our sample with Olek architecture, and we successfully replicate or achieve the key twist cracking mechanism in small scale. So, and we didn't sacrifice the strength. We didn't intended make the interface weaker. We just used the normal printing process and achieve the key mechanism. And the next step is to want to scale it up to a large scale, which we will have we will have enough layers and interface. So we will promote the micro crack development to improve the toughness and energy absorption capacities. And the other architecture we also start to look at in small scale is the Harriman architecture. So this is relatively new in 3D printing concrete, because typically when we print concrete, we print in X and Y plane, and we build up in Z plane. So for this architecture, we need to study how to print in a 1D surface, and then we scale it to a sinusoidal surface to achieve the filament shape of this architecture. And then we scale this to a 3D surface where we really active print X and Y and Z with the sinusoidal architecture and with the rotation of each layer to make it really closer to the real structure found in nature. So we study a little bit on how to print. We study a little bit of the two paths, and if you see these two pictures look different because they are generated by two paths. The left one are just follow the sinusoidal two paths. You can see it's become flatter and flatter and flatter as we build up. The red one, we modify the two paths. We modify the two paths to let our sample to maintain the sinusoidal shape as we print, so it can be more and more closer to the real structure we found in nature. And we also run some mechanical testing in small scale, and we test the Harriman architecture, cast sample, and Boolean architecture, and we found that the Harriman architecture performed really well on the compressive strength and work-out failure. It can improve both of the properties. So which bring us an opportunity to scale it up to test the energy absorption capacity of this architecture. So then I'm going to talk about a little bit about our large scale work. Thanks to this project, we start to design our extruder for the 3D printing system, and we put together extruder with the shear mixing in the extruder head, and we start testing the extruder with a large scale wall. So we built this wall to 3 foot tall, and overall we built the system. It's a relative new system to us. We start learning and we start building a system and we start printing large scale. So now use what we learned in this printing process. The next step is we are going to do is to scale up the architect material, architect concrete. So because in the simulation, we found that if we increase the volume of the sample where we got enough interface, so it will promote the micro crack development to increase the toughness and energy absorption capacity. So we can scale this up to large scale, and we scale this up to test the energy absorption capacity which can be potentially used for the roadside barrier applications. But large scale is more complex than small scale. We need to start with material development, and then we need to study the two-pass design, and then we conduct the mechanical evaluation. So we also start with the material development, which for 3D printing concrete, we also want our material to be more cost effective, because as I mentioned before, the current solutions are suffer from high cost. But we are also target of make our 3D printing concrete like cheaper. So for 3D printing concrete, the expensive component is the admixtures, like we was discussing modifier admixtures. And we are studying to replace this admixture with the cost-effective, like natural admixture is a cellulose nanofiber. And we are also studying to replace the cement partially with limestone failure. So we run some rheology testing, so which it shows that the cellulose nanofiber can be a really effective viscosity modifier by increase the static yield stress and viscosity. So it can increase the static yield stress by 3,500 per percent weight of CNF. Just in comparison, nanoclay is also another studied like admixtures in the 3D printing concrete field. It can only increase 400 Pascal per weight of the nanoclays. So also additional limestone failure can also enhance the static yield stress, which really help the buildability of the 3D printing concrete and reduce the cost in the meantime. So then we also will study the two-pass design for 3D printing concrete, because for the robotic arm in large scale, we have multiple access. So which means we have the room to use the multiple access to print sinusoidal architecture in different nozzle configurations. It can be perpendicular to the support base. And the last step is we are going to evaluate the mechanical performance, specifically the impact resistance and energy absorption capacity of the large scale architect concrete, and which can be potentially used for roadside barrier applications. These are my reference, and that'll be it. So I'm open to any questions. Thank you.
Thank you. Very interesting work. Any questions to Yo?
I can ask one if I may. This is Pinar here. Very interesting work, thanks. Are the barriers typically reinforced?
Yes.
Okay, so just curious, what's your strategy for reinforcing it, or maybe it won't be reinforced in the traditional way that we think?
It could potentially be reinforced in the traditional way. That's one way we can do 3D printing. So we can place rebar manually or automatically during the 3D printing process. So you just have to we need to design the two-pass and design the way we place reinforcement. The other way is alternatively, we can use fiber reinforce. So it is relatively easier for the 3D printing process. And yeah, these are the two ways potentially can be used for reinforcing.
Okay, thank you. I know it's always a challenge with 3D printing.
Yeah, it's a challenge.
So,
yeah.
Okay,
Thank you.
Excellent presentation. I have one quick question. Again, this is an amazing technology. I think it has great potential, and you gave us today a great overview of, first of all, the capabilities that you guys have in your lab, which is an amazing thing. I love the video when you guys were printing the curved wall. I know that you probably have looked into since the title of the project is Bio-Inspired, so you looked at many examples from nature, and you're trying to mimic them in your project, which is amazing. Now, in your examples that you went through in nature and you studied, did you see only that the architectural design of the components or the elements or the members is the main difference, or there is some associated with it also some variability in the material properties, like the density of the material, for example, or the nature of the material, not only the architecture? So basically, both are changing together, or maybe in some cases, one is changing and not the other. So can you please comment on this?
Yeah, thank you, Professor. like you are right, in the nature, they are like in the nature, the material are leveling the material properties and the lightweight. So basically, so they're level in, maybe we can come back to this slide. Sorry. Here. So in the nature, there are a lot of material can have the like reasonable strength, toughness, and stiffness. And then in the meantime, because they are developing for like they are like they are developing for over 1,000 years. They are also have the capability to make it more lighter, like lightweight. So, but in our study, we haven't go that far yet because we are start study with the damage mechanism and we start study with the architecture. So it's a good point to go like evaluate more after we like really like replicate this structure and damage mechanism. Then we start with we get the material with higher like strength, higher toughness, and in the meantime we can make it lightweight. So
Yeah, excellent. Thank you.
thank you.
All right, any other question? Can I ask a question about the printer itself? This is like, commercially available that can, and does it require special installations in a lab facility on campus? What are the ingredients that you've been using to build the wall? Is it a regular mix or a special mix?
Oh, sorry, your question is the printer or the mix?
The printer and the concrete that you used.
Oh, okay. So the printer is we bought this robotic arm, and we bought this pump. Basically, those are like commercial available, but we built this like extruder with another postdoc like in our group. So we incorporate the shear machine capacity in the extruder, and then of course we like build our own concrete base and we own support on like metal plate to prevent the rollover of the robotic arm. And for the material, we are developing a mixture that could be more cost effective and more sustainable. Like basically for 3D printing concrete, the most important and most expensive parts are cement and admixtures. So we are trying to improve this to replace cement with some like with limestone failure to some extent. And also we are trying to replace the expensive commercial available admixtures with some more natural source admixtures. Like say we are trying to use cellulose nanofiber. It's kind of more cost effective than the commercial available admixtures. So we are developing our own materials. So.
Oh, thank you.
Yeah, thank you.
All right. If there is no other questions, that's the conclusions of our webinar today. I would like to thank everybody coming in today. And I'm not sure, Chris, do we share the PowerPoints to the participants?
We haven't been sending the PowerPoints. We've been loading on the TRANS-IPIC website the presentations.
Okay, so I encourage everybody, if they wanted to take another look in the PowerPoints, to go check our website and download those PowerPoints. All right. With that being said, I'd like to thank everybody and enjoy the rest of your day.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Thank you.
Thanks, everybody.